Hello, welcome to our STEAM projects based on the Raspberry Pi Pico and MicroPython. These lessons are designed for the somewhat experienced STEAM teacher. We call the second level the SHERPA level. In our project number 2, we are going to use Pulse Width Modulation to dim an LED. My name is Peter, I am the founder of Educomondo and a certified STEM instructor and course developer. The goal of today is to take a guided tour around the Raspberry Pi Pico and to build the starter kit project, the dimming table lamp, which will teach us how to read and interpret analog values in MicroPython. Let's start with a guided tour of the Pico. The Raspberry Pi Pico has a row of 20 pins on each side, or 40 pins in total. Of those 40 pins, 26 are programmable GPIOs, or general purpose input-outputs, that you can use to connect peripherals like LEDs, motors and sensors, or even establish a communication with other microcontroller boards. As said, GPIO is short for General Purpose Input-Output. Unlike the Arduino Uno, the Raspberry Pi Pico GPIOs are labeled on the back. When you use the Raspberry Pi Pico on a breadboard, it is difficult to identify each pin. So, it's handy to always have this pinout diagram by your side. You can download it from the official Raspberry website. So let's take a closer look at the main pins. The 26 GPIO pins are colored in a light green on the diagrams. They are numbered from GPIO 0 to GPIO 29. 4 of these pins are not connected to a pin header, but are dedicated to internal board functions. And those pins are the GPIO 23, 24, 25 and 29. For the moment, we only need to remember that the GPIO 25 is connected to the onboard LED. All Raspberry Pi Pico GPIOs can output Pulse Width Modulation signals. Indeed, PWM stands for Pulse Width Modulation. If you are not familiar with the principles of PWM, please go to our Arduino microcontroller lesson first, called the Twinkling Star. The Pico has a 12-bit ADC. An ADC stands for Analog to Digital Converter on a fixed set of pins. This means it can transform an analog signal into a digital signal as a number ranging from 0 to 4095 or 2 to the power of 12. It has 5 ADC channels, but only 4 are accessible on the GPIOs, namely numbers 26, 27, 28 and 29. The first 3 GPIOs, so 26, 27 and 28, can be used to read voltage from peripherals. GPIO 29 can measure the input voltage or VSIS that powers the board. The 5th ADC channel is connected to the built-in temperature sensor. You will also notice that quite a number of GPIO pins can be used for I2C peripherals or I2C peripherals. The pins 4 and 5 are the default pins for the I2C data and clock signals. Now we are ready to start our first project running on the Pico. The goal is to read the value from a potentiometer in order to dim an LED. This is the large breadboard with the Pico installed and the pinout reference card. Because the Pico is installed on the breadboard, we prefer to use the 800 holes or full-sized breadboard. You can still use the 400 or half-size version, but it will be a bit high to install all components. This is the potentiometer, and for our demonstration I have taken a larger version than the one that is in the Key Studio Starter Kit, but functionally they are exactly the same. We covered in detail the working of the potentiometer in the Arduino course, but if you need to refresh this to your students, I suggest you refer them to lesson 18 called the car speed dial. Next we need a red LED and a resistor. For your students, this is a good rehearsal of Ohm's law. Let them calculate the required resistor value for the red LED when the voltage is not 5 volt like the Arduino, but 3.3 volt. The power consumption of a red LED, as you might remember, is around 20 milliamps, so 3.3 volts divided by 0.02 gives us around 165 ohm. You can still use the 220 ohm, but the LED will not light up as brightly. For this project we will use our box of preformed cables, and we will start by making a connection between the 3.3 volt out pin, or number 36, and the positive rail of the breadboard. The same for connecting one of the ground pins to the negative rail. Now we install the potentiometer on the breadboard, connect the outer pins to the positive and negative rail, and because we will read values from the middle pin of the potmeter, we use a data wire connecting to the ADC 0 or GPIO 26. The red LED is pushed into the breadboard, and then you can connect the short leg or the cathode to the negative rail. The long positive leg or anode is connected via the resistor to GPIO 2. Checking our reference card, this is the 4th pin. Open Thonny and create a new file. The first step is to import Python libraries, or often called modules. You can either import complete modules or select certain classes. In this exercise, we will only import what we need for the program. So we type from machine import, and we will need 3 classes, namely ADC, PWM and pin. The machine library is probably the most used as it contains the typical commands to address the microcontroller's functions. In this case, we will use the analog to digital converter, the pulse width modulation, and the pin classes. Because we will also need some delays, and in Python or MicroPython, we will use the following command from time import sleep. This is the Python's way of defining a delay. And just like we did with the Arduino, we will give the pins a name. So ADC pin equals 26 and LED pin equals 2. Now, again, very much like with the Arduino libraries, we first need to create objects from those libraries. So we create an object pot, which is short for our potentiometer, potmeter, equals in capital letters ADC and in between brackets ADC pin. And we also use the object, or we create the object PWM equals in capital letters PWM, and in between double brackets we first say pin, and then we refer to the LED pin, which we defined previously here as number 2. Now, for the LED to work, we also need to define the frequency, which is set standard at 1000. So PWM dot frequency, short for frequency, FREQ, and in between brackets 1000. Now we write a program to go on forever while it is true, and when it's true, it's true. So while true, ADC underscore value equals pot dot read underscore U16, open and close the brackets. So what does this mean? So the ADC value is what we read from the object pot. And we will see that because we use MicroPython, the input is extrapolated to 16 bits or 2 to the power of 16, which is 65,536. So U16 refers to a number between 0 and 65,535. Why? Indeed, 0 is position 1. To check the reading, we can monitor this in the REPL or the shell space of Thonny. So print, and in between brackets, we print the value ADC underscore value. Now, the duty cycle of the PWM is based on the ADC underscore value, the reading of the pot object. So PWM.duty underscore U16, and in between brackets ADC underscore value. And we introduce a delay of 100 milliseconds or 1/10 of a second. Note that in MicroPython the delays are expressed in seconds, so that is slightly different from what we have seen with the Arduino in the past. So sleep and in between brackets 0.1. Okay, well, let's upload the code and check whether everything is working properly. If it doesn't, no panic. You can do some logical fault finding. Were there any error messages in the REPL or in Thonny? Did you select the right Raspberry and comms? Did you connect the components to the right GPIOs? Has the LED been mounted correctly, taking the polarity into account? Were there any loose wires or legs? Or maybe you're just unlucky and one of the components is broken. And that's it for our second lesson. I hope you and your class enjoyed it. For our third lesson, we are going to introduce an LDR, which stands for Light Dependent Resistor. After that lesson, you will be able to control the switching on and off of an LED depending on the ambient light. Looking forward to welcome you again, and bye bye for now.